Hello everyone, myself Pranavi, Assistant Professor, Electronics and Telecommunication Department of SIU's Graduate School of Technology. Today I'll be explaining about the emitter bias circuit. The DC bias network which we have learned in the fixed bias circuit. There we have found out that stability factor S is equal to 1 plus beta, which is very high. So to reduce the stability factor and to increase the stability, we are going to introduce a feedback resistor, which is RE in the emitter to ground path, so that we will find out what is the stability factor by adding this particular emitter resistor, and uh, what is the advantages of adding this emitter resistor. So let's begin. So we are I'll first of all draw the emitter bias circuit. My transistor, and I'm having emitter resistor RE, base terminal and my collector terminal. So I'll term this is base, collector and emitter. This is my NPN transistor. This is resistor RE. Fixed bias circuit contains base resistor RB and collector resistor RC. To this, I am going to add the supply, which is VCC. The current through this is IC. Here the current is IB. Resistor is RB. Resistor is RC. And emitter terminal which is connected to ground, and current through this particular terminal is I. As per our last video, our analysis says this is my reduced, or this is my DC equivalent fixed bias circuit. So to this, I am going to apply the input loop. Input loop I am going to apply between base and emitter terminal. So I'll draw only base and emitter terminal part. So whatever is connected to the base and whatever is connected to the emitter should be included in this loop. So my emitter is connected to the resistor RE. Through this, my current is I. My base terminal is connected to resistor RB, which is further connected here, which is further connected to VCC. So this VCC, I'll directly draw it as positive, negative, positive, negative, and this is my ground terminal. So I'll just mark all the corresponding currents. This is my current IB, and this voltage we are going to consider as VBE. So as per our concept, I'll apply the loop. For loop, I'm going to consider as start from one ground point and end into the another ground point. So whatever parameter I am coming across in this path, that I am going to write down for my input loop. So my input loop contains plus VCC minus IPRB minus VBE minus IERE is equal to 0. I'll repeat, plus VCC minus IPRB minus VBE minus IERE is equal to 0. VCC minus IPRB minus VBE minus IERE is equal to 0. From input loop, we are supposed to find out the IB. So this, first of all, RE, we have to convert it in terms of IB. So RE, which is equal to IB plus IC. But my IC is equal to beta IB. So my IE is equal to 1 plus beta multiplied by IB. This value of I am going to substitute over here in the input loop. So when I substitute this, in the expression, I'm going to get as VCC minus IBRB minus VBE. In place of I, I'll write down now as 1 plus beta times of IB into RE, which is equal to 0. I'll take IB terms on one side and voltage terms on another side. So I'll get VCC minus VBE IB RB plus 1 plus beta times of IB into RE. I'll take IB common from here. So in bracket, I am going to get it as RB plus 1 plus beta times of RE, which is equal to VCC minus VBE. So from this, I am going to get my IB, which is equal to VCC minus VBE divided by RB plus 1 plus beta times of RE for emitter bias circuit or a fixed bias circuit with the emitter resistor. So this is what my input loop or input part is. When after calculating IB, when we have the value of IB with us, we will calculate IC. So this IC is equal to beta IB. Now we will apply the collector emitter loop or your output loop. So collector emitter loop or a output loop. So collector emitter loop or a output loop we are going to apply. We will consider all the parts which are connected to the collector and emitter. So when we will apply the loop, output loop, or I'll say collector emitter loop, whatever is connected to the collector and whatever is connected to the emitter will come into the picture. So here I am having transistor. Emitter is connected to emitter resistor and then it is connected to ground. And collector is connected to the resistor RC and from there it is connected to VCC. RC, RE. Current through this is IC. Current over here is IE. And here we do consider plus minus VCE. This is VCC. Our concept says apply loop from one ground point to another ground point. So I am applying the loop from one ground point to another ground point. What I am observing over here is plus VCC minus ICRC minus VCE minus IERE is equal to 0. So I'll get plus VCC minus ICRC minus VCE minus IERE is equal to 0. Here in the output loop, we will put IE is equal to IC. So it is VCC minus ICRC minus VCE minus ICRE, which is equal to 0. From this, we are supposed to calculate VCE, which is equal to, I'll transfer this VCE to other side, I'll get VCC minus, I'll take IC common, it will be equal to RC plus RE. This is what my VCE expression. After this, next part is to draw the DC load line. DC load line. DC load line is to be drawn on the output side. So for this, we are going to consider expression VCC minus VCE minus IC into RC plus RE, which is equal to 0. Put VCE is equal to 0. Put IC is equal to 0. When I'll put VCE is equal to 0, I'll get my IC, which is equal to VCC upon RC plus RE. And when I'll put IC is equal to 0 in above expression, I'll get VCC, which is equal to VCE. These two are acting as end point of my DC load line, where center point is my Q point. So when I'll draw the DC load line, which is VCE versus IC on the output characteristics graph, my one end point is VCC upon RC plus RE. Another end point is VCC. I'll draw this line and center point will act as my Q point. So this is my DC load line analysis. And last part left is stability factor, which is defined as S is equal to 1 plus beta upon 1 minus beta into dou IB by dou IC. So when I need this dou IB by dou IC, I need to calculate, or I need to focus on my input loop. So here my input loop is this VCC minus IBRB minus VBE minus IERE is equal to 0. I'll write down that loop again. My input loop, which is equal to VCC minus IBRB minus VBE minus IERE is equal to 0. Here I'll substitute E as it is IB plus IC for the stability factor. So VCC minus IBRB minus VBE minus IB plus IC into RE, which is equal to 0. So I'll get VCC minus IBRB minus VBE minus IBRE minus ICRE, which is equal to 0. I'll take IB common and I'll transfer that to the other side. So I'll get VCC minus VBE minus ICRE, which is equal to IBRB plus IBRE. Means I am transferring these two terms on the other side. So my expression says find out dou IB by dou IC. That means I need to take this expression in terms of IB only, which is equal to IB into RB plus RE. So my IB is equal to VCC minus VBE minus ICRE upon RB plus RE. Now I'll take the derivative with respect to IC. So I'll differentiate this with respect to IC. So here we can see that my VCC is constant, my derivative will be 0. VB is constant, my derivative will be 0. Derivative of IC with respect to IC will be 1. So I'll get, that is dou by dou IC of RE upon RB plus RE. But this is minus, so I'll put over here minus sign. The answer comes out to be minus. Derivative of IC with respect to IC will be 1 minus RE upon RB plus RE. That is my answer for dou IB by dou IC. So I'll substitute this value in stability factor expression, which is equal to 1 plus beta upon 1 minus beta into dou IB by dou IC, which gives me 1 plus beta upon 1 minus beta dou IB by dou IC is this RE upon RB plus RE, but with minus sign. So the value comes out to be 1 plus beta upon 1 plus beta into RE upon RB plus RE. So here we can see that my denominator compared to my fixed bias circuit has increased. So when my denominator is increased, definitely my numerator value going to be reduced, and hence I can confidently say that my stability factor is reduced by adding the emitter resistor in the fixed bias circuit, and hence my emitter bias circuit gives the improved stability compared to the fixed bias circuit.